Welcome to Deep Space Drift. Tonight's calm journey follows light as it stretches across distance and reveals how the universe's true scale quietly reshapes what can be seen and what fades into the cosmic night. Settle in for a slow, science-led drift through vast structures, gentle limits of observation and deep time. If this kind of space storytelling helps the mind unwind, tap, like, subscribe and turn on notifications for more long-form sleep documentaries from the dark, quiet edge of reality. The first hint of true scale arrives as a softness at the edge of visibility. That softness comes from light that travels so long that the universe grows during the journey. A quiet patch of darkness holds countless dim ovals. Each one has a brighter core and a fading halo. The edges blur into a grainy background. Some shapes show a faint inner gradient like a pale ember cooled into charcoal. The scene does not feel crowded. It feels deep. Distance does not look like a line. It looks like layers of dimness stacked behind layers of dimness. In that layered view, time hides inside space. A signal would leave a young region and arrive after ages. The arrival carries a built-in timestamp. The timestamp sits in the color of the light. The calm surprise is that color becomes a ruler. The ruler is not held by any hand. It is carried by the wave itself. A slow payoff settles in. The farthest lights are not only far away, they're also far back in time. A second image forms alongside the first. It is not a picture of objects. It is a picture of a wave train crossing emptiness. The crests are evenly spaced at first. Then the spacing lengthens. The wave does not break. It simply stretches. Redshift is light stretched as space expands. The stretching is gentle. It is also relentless. A thread of honey falls and thins as it descends. The thread grows longer without adding more honey. In the same calm way, a light wave grows longer without adding more light. The change matters because a longer wave carries less energetic color. Blue slides toward red. Visible slides toward infrared. The oldest light becomes warmer in tone. It becomes easier to miss. Another payoff arrives without label. The shift in color is not decoration. It is a measure of how much the journey space has grown. The first visual anchor returns to the dim ovals. Their glow is not evenly spread. The center is tight. The outer light fades in a smooth slope. A faint ring-like contour sometimes appears where brightness drops faster. That ring is not a boundary in matter. It is a boundary in sensitivity. It marks the point where faint becomes too faint. Even this edge is part of the story. It hints that the scene is incomplete. It also hints that deeper scenes exist behind it. At this distance, faintness is not only weakness, it is age. Another slow picture opens. A veil of dust drifts through a region between bright sources and darker voids. The dust does not shine strongly, it scatters and absorbs. Shorter wavelengths strike the grains and do not pass cleanly through. Longer wavelengths slip through more easily. The veil has texture. It shows wisps and thicker knots. It shows a soft shadow where the dust is densest. In that shadow, visible light would fade away. Infrared light can still pass. The veil becomes less like a wall and more like a curtain. A payoff settles in. Some of what looks like emptiness is simply hidden behind scattering. When longer waves pass, structure appears where smooth darkness seemed to be. This is one reason the universe feels larger. The visible portion is not the whole portion. The idea of size expands when hidden regions become countable. Now the scale shift begins quietly. The scene moves from a single galaxy glow to the journey of its light. The journey lasts about 13 billion years. That span is like a beach made of years. Each grain stands for a single year. The beach stretches beyond the horizon. Yet the journey is not only a long time, it is a changing distance. While the light travels, space itself expands. The starting point and the end point drift farther apart during the flight. The travel time stays the same. The present separation grows larger than simple travel intuition suggests. Another payoff appears. The universe can be older than the travel time implies. It can also be larger than the travel distance implies. The difference comes from expansion happening during the transit. A fresh visual anchor appears as a set of nested shells, not shells of matter, shells of arrival times. Each shell is a layer of space from which light reaches the present at the same moment. The nearest shell is sharp, the farthest shell is faint. Each step outward is also a step backward. The shells do not sit still. They widen as expansion continues. The pattern turns the sky into a depth map. It is not a map of geography. It is a map of history. In that map, a small point of light can belong to a huge volume. The scale feels calm and immense at once. The limit of intuition enters here softly and precisely. The mind expects distance to behave like a road. It expects a fixed length that can be measured the same way at all times. Expansion breaks that road picture. There is no single meaning of distance that fits every purpose. There is light travel distance. There is present-day separation. There is distance tied to how large an object appears. These distances agree nearby. They drift apart at great range. Another limit appears in observation itself. At extreme faintness, a dim source can mimic another source. A smooth red glow can come from great age. It can also come from dust and cool temperatures nearby. At the edge of detection, the difference is subtle. The wavelength range is limited. The signal is weak. Uncertainty grows like fog thickening at dusk. The deepest claims must be checked against multiple clues. Another payoff lands. True scale is not a single number. It is a consistent story told by many small measurements that agree. The visual anchor turns once more to a single stretched wave. The crests are farther apart now. The amplitude is lower. The wave arrives as a whisper of heat in darkness. It carries a message that does not speak. It measures. It indicates expansion without shouting. It indicates age without a clock face. It indicates distance without a ruler. The quiet conclusion of this opening is simple. The universe looks larger when time is visible in light. The universe looks larger when expansion is treated as part of distance. The next steps deepen that ruler of colour. Redshift becomes more than a warm tint. It becomes a way to place objects on the layered shells of time. The journey continues by following how stretched light turns the sky into a calm scale. A gentle gradient in light can hold more distance than any sharp edge. The gradient matters because stretched colour reveals how much space grows during a journey. In a quiet region, a faint glow spreads from a pale centre into a softer outer haze. The light does not arrive as one uniform tone. It arrives as a slow drift from shorter waves to longer waves. The drift is not an ornament, it is a measure. At this distance, light behaves as a message that changes shape while it travels. The change is smooth, like ripples that widen as they slide across a still pond. The crests grow farther apart. The pattern stays recognizable. A small payoff settles into place. When spacing between crests grows, the universe has expanded during the crossing. The scene becomes more concrete when the light is imagined as a long ribbon. Along the ribbon, brightness rises and falls in gentle bands. Some bands are slightly darker. They appear as thin notches that cut into the glow. The notches do not look dramatic. They look like shallow valleys in a wide dune field. Each notch is narrow. Each notch is placed at a specific position along the ribbon. The position shifts when the ribbon is stretched. A second payoff arrives. Those small notches can serve as anchors even when the overall glow is faint. A definition comes quietly. Wavelength is the distance between repeating peaks of light. Longer wavelength means peaks sit farther apart. Shorter wavelength means peaks sit closer together. In that sense, redshift is a longer spacing that was not always so long. A Y appears without strain. Spacing can be measured even when brightness is low. The ribbon view slows into another visual anchor. A dark background holds a set of parallel bands. Some bands are bright, some are dim. Between them sit fine transitions where brightness slopes gently down. The slopes feel like shallow ramps. The edges are not sharp. That softness matters. It shows that a distant source is not a simple lamp. It is a mix of many processes. Some parts glow strongly, some parts are muted by intervening matter. A small payoff lands. The pattern of bands carries information about what the light passed through, not only where it began. Now the idea of stretching becomes a careful checkpoint. A light wave leaves a young region with a certain spacing. It travels through emptiness that is not static. Space expands. The wave still moves at the same fundamental pace. Yet the distance between peaks grows as the distance between points in space grows. The wave arrives longer. It arrives redder. If the wavelength becomes about 10 times longer, the expansion during travel is about tenfold. That number is large in a quiet way. It is like a short rope that becomes a long rope without adding fibre. The rope only changes because the gap between its markings increases. A payoff settles. Redshift is a direct clue about the scale of expansion between then and now. The ribbon of light carries this clue without needing a separate clock. The notches in the ribbon become more important here. The notches are not random. They come from specific energies that certain atoms and molecules absorb. A definition fits within a single breath. A spectral line is a narrow dip where light is absorbed. The dip acts like a marker on the ribbon. The marker shifts as the ribbon stretches. Two examples follow in plain imagery. A musical note sounds lower when its wave is longer. A pond ripple looks wider when crests are farther apart. In the same spirit, a light wave looks redder when its spacing grows. The importance arrives in one sentence. Those dips allow distance to be inferred without needing the source to be familiar. Another visual anchor forms in a calm arrangement. A cluster of faint ovals sits in a field of darkness. Between them the background is not uniform. It has a mild grain. It has tiny specks that appear and vanish with attention. Over the field the ribbon pattern is imagined as hovering. Each oval contributes its own ribbon. Some ribbons are slightly different. Some have deeper notches. Some have smoother slopes. A payoff settles. Distance is not guessed from shape alone. It is anchored by the shift of markers in the light itself. The scale shift deepens. Near space, redshift is modest. The ribbon shifts only a little. Markers move a small distance along the band. Farther out the shift grows. The markers slide so far that familiar parts of the ribbon move into infrared. That move is gentle. It is also decisive. It means the oldest light becomes harder to see in the same range. In that region, light behaves as if it is retreating into longer waves. A payoff appears. The observable universe is shaped by which waves can still be caught. Some histories are hidden because their light has slid beyond easy reach. The limit of intuition arrives softly and clearly. Redshift can resemble simple motion at first glance. The mind expects a source moving away to look redder, like a receding sound that lowers in pitch. That picture is incomplete at the larger scales. Expansion is not a single object moving through space. It is space itself changing. The difference matters because it changes how distance is defined. It also matters because it changes how the same redshift is interpreted across time. A second limit enters in the act of inference. Notches can blur when the source is faint. Notches can be masked when dust smooths the ribbon. Notches can be confused when different features overlap after shifting. The uncertainty is not dramatic. It is like trying to follow a faint trail after wind softens the edges. The trail still exists. The boundary between trail and ground becomes less clear. Another payoff settles. Confidence comes from multiple consistent markers, not from a single dip. A new visual anchor appears as a thin veil in front of a glow. The veil has fine layers. It shows a gradient from thin to thick. Where it is thickest, the glow behind it is muted. The edge of the muted region is soft and curved. It is not a hard cut-off. Light scatters around the denser knots. The scattering makes a faint halo. The halo is broader at shorter wavelengths. It is tighter at longer wavelengths. A payoff arrives. The same veil that hides some color can reveal itself through the way halos widen or narrow. In that region, the ribbon is not only stretched, it is also filtered. That filtering must be separated from stretching. The calm method is to look for markers that filtering cannot imitate. Markers shift together when stretching dominates. Markers change depth when filtering dominates. This separation is not perfect. It is workable. It produces a distant story that can be tested. Another scale shift closes in gently. A single notch in a ribbon is a tiny feature. It is smaller than the width of the overall glow, yet that notch can place an object within a vast shell of time. A narrow dip becomes a guide to billions of years. A small payoff settles as a quiet bridge. When distances can be placed with such markers, the early universe stops being a vague darkness. It becomes a layered scene with chapters. The next step naturally follows. Once those chapters are placed, the shapes inside them can be examined. Some shapes appear too orderly for their age. The journey moves onward with that calm tension held steady. Some of the earliest galaxies appear with edges that look already settled. The quiet meaning is that structure can form quickly when gravity and cooling cooperate. At this distance, a faint oval glow shows a bright core. A thin outer skirt fades into darkness. The light is not smooth everywhere. Small knots sit along the oval. Each knot has a sharper boundary on one side. Each knot has a softer tail on the other. The scene suggests motion without showing motion. The core looks compact. The outskirts look delicate. A first payoff settles in. When a distant galaxy shows a core and a disk-like outline organization is already present. That organization does not require long ages. It can emerge from simple rules applied early. A slow visual anchor deepens. The oval has a subtle gradient. The center is dense and pale. The gradient relaxes outward in gentle steps. Along one side, the light seems slightly thicker. It forms a narrow ridge across the middle. The ridge does not look like a line drawn on purpose. It looks like a region where more stars share a common plane. The physical detail is quiet and specific. A flattened shape hints at rotation. The outer boundary is not sharp. It dissolves into a faint halo. Another payoff arrives. A flattening suggests that spinning is already sorting matter into layers. Rotation becomes the first concept. Rotation is the turning of matter around a shared center. When gas falls inward, even a small twist can grow. The twist strengthens as the gas shrinks. The effect is like a whirl of leaves gathering into a ring. The leaves are not needed here. Only the pattern matters. In plain terms, falling inward can amplify a gentle spin. That spin resists collapse in one direction. It encourages a disc-like form. The why is simple. A disk spreads mass outward. It changes how new stars form across a galaxy. A second visual anchor appears as a set of clumps arranged like beads along a dim arc. The beads are uneven. Some are brighter, some are barely there. Between them the arc is faint but continuous. The arc feels like a stretched band of glow. It is not the ribbon of light. It is a shape of matter. The band curves slightly. The curvature is subtle. It implies a slow orbit. A small payoff settles. Clumps placed along an arc are often a sign of gas that fragments while still rotating. Fragmentation is the second concept. Fragmentation is breaking into clumps under gravity. Gas cools and loses pressure support. It can then gather into denser pockets. Those pockets brighten when stars form within them. The process is not orderly at first. It is patchy. It still follows a calm pattern. Dense regions pull more matter in. They become denser still. The importance is direct. Fragmentation can build structure without waiting for perfect smoothness. Now the section's main number arrives in a quiet scale shift. Some of these organized shapes appear within about 500 million years after the beginning. That span is like the first half hour of a very long day. The comparison holds the feeling of early timing. A half hour can still contain weather changes. A half hour can still contain sudden settling after a storm. In cosmic time, a few 100 million years can still contain rapid assembly. Another payoff lands. Early does not mean empty. Early can mean fast. The sandbar analogy becomes the main everyday bridge. A river carries sediment in a restless flow. When the flow slows, a sandbar can appear quickly. The bar has an edge. It has a crest. It has a gentle slope downstream. It is shaped by steady forces acting on loose grains. In the same calm way, gravity and cooling shape loose gas. When conditions allow matter piles into a stable form, the bar does not require careful planning. It requires a flow and a place to settle. A galaxy does not require long preparation. It requires gas that can cool and a field that can gather it. The physical details match. A bar has a ridge and a fading tail. A young galaxy can show a dense center and a faint outer skirt. Another visual anchor slows into a close look at the core. The core is not a single point. It has a rounded profile. Brightness rises steeply, then levels off. A soft shoulder appears before fading outward. The shoulder looks like a boundary in density. It suggests a central concentration of older stars or thicker gas. The edge of the core is smoother than the clumps. The clumps are sharper. A small payoff settles. A smooth core beside sharp clumps hints at two timescales. One part forms steadily. Another part forms in bursts. The limit of observation enters gently. At great distance, the smallest structures blur. The clumps can merge into one another in the image. The disk can look thicker than it is. The true edge can hide in faintness. In addition, mass is not seen directly. It is inferred from light. A mass-to-light ratio is the amount of mass per brightness. That ratio depends on age and dust. Dust can dim and redden light. Young stars can shine strongly for little mass. Both effects can mislead. The limit is clear. A compact bright galaxy can seem more massive than it is. A dusty galaxy can seem older than it is. Another payoff arrives. A surprising early structure does not always mean a heavy early structure. It can mean the light is weighted toward bright youth. It can mean the outer parts are too faint to detect. It can also mean growth truly is efficient. The story is tested by looking for consistency across many galaxies. The clumps appear again in different places. The cores appear with similar steep profiles. The outer skirts vary. Some skirts are wide, some are barely present. This variation matters. It suggests that early assembly is not one single path. It is a family of paths. Some regions gather matter into tight forms. Some spread it out sooner. The scale shifts outward now. A single galaxy fills a tiny patch of sky, yet it sits within a large volume. Many such galaxies appear across the field. Each one is a different stage of early settling. Together they hint at a broader environment. Gas flows along filaments. Dense knots grow at crossings. Rotation and fragmentation sculpt what the flows deliver. Another payoff settles. Order emerges from repeated simple steps. In that calm order, an even stronger mystery begins to show. Some cores are so concentrated that ordinary star formation may not explain them alone. The next movement follows the core inward. It follows the idea that extreme central brightness can signal an even deeper engine. The transition remains soft. The scene drifts from disks and clumps toward the densest centers. A single bright point can sit inside a young galaxy like a steady lantern in thin fog. That point often marks a compact engine where falling gas turns gravity into light. At this distance, a galaxy's outer glow looks soft and wide. Near the center, the light tightens into a sharp core. A faint halo surrounds it. The halo fades in smooth steps like mist thinning with height. In some cases, a darker crescent cuts into the halo. The crescent is not empty space. It is a shadow made by dust that absorbs and scatters shorter waves. The scene holds a quiet physical geometry. A bright center, a layered envelope, a curved notch of dimness where material lies in the way. A small payoff settles. A central glare paired with a dust shadow suggests two things at once. Something bright is compact. Something opaque is arranged in a partial ring. Light behaves as a traveller that can be blocked by fine grains. Longer waves pass more easily. Shorter waves fade sooner. The bright core remains visible because the emission is strong and because some paths through the dust are thinner. The halo looks smoother because scattered light spreads into a wider glow. The first checkpoint arrives as a simple idea. The center is not merely crowded with stars. It can be powered by gas falling inward. A definition comes softly. An accretion disk is gas spiraling inward in a thin, hot disk. The disk forms because even a small spin becomes stronger as gas contracts. The disk heats because collisions and friction convert motion into thermal energy. The heat then leaves as radiation. The importance is quiet and direct. A small amount of gas can produce a great deal of light when it falls deep. A visual anchor deepens into a close view of the core. The core is not a perfect point. Its brightness rises steeply, then rounds off near the center. The outer edge of the core has a subtle shoulder. The shoulder suggests a transition from very hot inner regions to cooler outer layers. Beyond that shoulder, a faint glow spreads outward. The spread looks like a soft skirt around a bright bead. In the darker crescent, the skirt thins more abruptly. The physical detail is gentle but telling. A partial ring of dust can shape the appearance without changing the source itself. Another payoff arrives. Brightness alone does not reveal mass. Shape and shading reveal structure. The main number enters with a calm scale shift. Some early central engines appear to hold about 1 billion times the mass of the Sun, like packing a vast galaxy's worth of mass into a region smaller than a typical planetary system. The comparison is not meant to sharpen the edge. It is meant to settle the mind on scale. Large mass can exist in compact space. Compact mass can control the motion of nearby gas. The gas responds by forming a disk. The disk responds by heating. The light responds by spreading through dust and darkness. A new everyday analogy becomes the guiding bridge. A warm spring under ice melts a round opening. Water rises and flows inward along curved paths. The hole stays open because heat keeps arriving from below. The surrounding ice remains because the heat is concentrated near the center. In the same calm way, a compact engine can keep a bright core open in observation. The surrounding galaxy remains faint because energy is concentrated at the center. The analogy holds a payoff. Concentrated power does not require a large visible area. It requires a deep source. The next checkpoint considers the glow outside the core. The halo is not uniform. It can show faint concentric layers. One layer is slightly brighter, then another slightly dimmer. These layers are not shells of matter. They are shells of temperature and opacity. Hotter zones radiate at shorter waves. Cooler zones radiate at longer waves. Dust filters the shorter waves. The result is a layered look, as if the center wears a thin warm cloak. A visual anchor appears as a gentle ring of infrared light. The ring is broader than the core. The ring has a smooth inner boundary. The outer boundary fades gradually. Along one side, the ring looks clipped where dust thickens. Another payoff settles. A ring of warm emission can be the dust itself heated by the central source. Dust does not need to shine like a star. It can glow faintly when warmed. This shifts the story from stars alone to environment. The engine and the shroud become one system. Gas falls inward. Light rises outward. Dust reprocesses the light into longer waves. The system becomes visible even when direct paths are blocked. The scale shifts again from the width of a dust grain to the width of a galaxy core. Dust grains are tiny, yet a dense sheet of them can dim an entire core. The dimming is not random. It follows geometry. Where a dusty layer tilts across the line of sight, a crescent shadow appears. Where the line of sight slips above the layer, the core appears clearer. A small payoff arrives. Shadows in deep space can be as informative as the light. They reveal arrangement, not only absence. The limit of observation enters softly and precisely. The disk itself cannot be resolved at this distance. The bright point is smaller than the finest detail the image can separate. Much of the disk must be inferred from how light is distributed across wavelengths. That inference has boundaries. Dust can mimic age by reddening light. Dense gas can hide parts of the spectrum by absorbing specific bands. In addition, faint halos can blend with background glow. The true edge of the halo can disappear into noise. The limit is clear. When the core is too bright and the surroundings too faint, the contrast can erase intermediate structure. Another payoff settles. Confidence comes from patterns that repeat across many objects, not from a single striking point. The story then returns to time. A compact engine this massive seems to require fast growth. Growth requires supply. Supply requires pathways. Gas must move from a wide region into a narrow one. That movement is not a straight fall. It is a series of losses. Gas must lose energy. Gas must shed angular momentum. The spiral tightens step by step. A visual anchor appears as a slow, inward whirl. Not a visible whirl in the sky, but a conceptual one. Outer gas forms a broad, faint sheet. Inside it, a denser lane curves inward. Closer still, the lane becomes a tighter arc. Near the center, arcs blend into a bright core where details vanish. Another payoff arrives. The same physics that makes disks also makes feeding possible. The spiral is not merely a shape, it is a route. Yet the route is not always steady. Dust thickens and thins. The core brightens and dims. The halo swells in longer waves when dust warms. These changes can occur on timescales far shorter than a galaxy's age. In that region, light behaves as a living record of recent inflow. The scale shift is gentle but large. Short variations ride atop billion-year growth. One moment can hint at a long history. The section closes by widening the view. If a central engine needs fuel, the fuel must come from outside the core. Outside the core lies the galaxy. Outside the galaxy lies the broader network that guides matter. The next movement drifts outward from the bright point. It follows the faint lanes and filaments that supply gas across great distances, and it keeps the tone slow and steady. Far from any bright core, darkness still carries a faint sense of direction. That direction comes from a vast web of structure that channels matter toward knots where galaxies assemble. In that region, a wide field looks almost empty at first, then thin threads emerge. They are not straight. They curve gently and taper at the ends. Each thread brightens slightly where it thickens. The thick places sit like small beads on a dim line. Between beads, the line fades but continues. The background remains dark and quiet. A soft payoff settles. When many faint lines aim toward the same point, the point is not random. It is a meeting place in a larger pattern. The main visual anchor deepens into a single filament. It looks like a pale strand stretched across a black lake. The strand is thicker in the middle. It thins toward both sides. Along it, brightness shows a gradient that rises toward a knot. The knot is rounder than the strand. Its boundary is not sharp. It has a smooth edge that dissolves outward. Around the knot, a faint haze forms a shallow halo. The halo has a gentle slope of light from center to edge. Another payoff arrives. A knot with a halo suggests depth. It suggests a region where gravity gathers material into a thicker pocket. A definition comes quietly. The cosmic web is a network of filaments and nodes across space. The filaments are elongated regions of higher density. The nodes are intersections where density is highest. The why lands in plain language. Matter follows the easiest paths set by gravity. Those paths often run along filaments into nodes. A simple analogy becomes the section's bridge. After rain-drying, mud forms a web of cracks. The cracks connect and branch. They widen where stress concentrates. Small islands of mud sit between them. The pattern appears without planning. It emerges from drying and tension. In the same calm way, the cosmic web appears from gravity and expansion. The web is not made of empty lines. It is made of regions that are slightly denser than their surroundings. Another payoff settles. A small difference in density can grow into a guiding skeleton. The scale shift begins with the smallest detail. A knot can be described as a compact glow within a faint halo. That glow spans a tiny angle in the sky, yet the halo implies an enormous volume. A single filament can stretch for about 100 million light-years like a crack that runs across an entire plane without leaving the same surface. The number is quiet but large. It places a thin thread across a space that dwarfs any single galaxy. Another payoff arrives. Long filaments mean that galaxies do not form as isolated islands. They form along lanes that connect. The scene returns to the filament's physical detail. The filament's brightness is not uniform. It shows slight thickening in places. It shows gentle bends where the thread arcs. The bends are not sharp corners. They are wide curves. The curves imply that matter does not fall straight inward from all sides. It streams along preferred routes. At this distance, light behaves as a tracer that rides on gas and dust. It outlines where material is thick enough to glow. The glow is faint. It is soft, yet it is coherent. A small payoff settles. Coherence across long distances signals an underlying structure stronger than chance. The next checkpoint considers motion without showing motion. If matter streams along a filament, a gradient can form. Density rises toward a node. Temperature can rise where gas compresses. The result can be a subtle change in brightness along the strand. One end looks slightly warmer in tone. Another looks slightly cooler. The change is mild. It is still meaningful. It suggests a flow of material. It suggests a slow inward drift. Another visual anchor appears as a junction where three filaments meet. The junction looks like a tiny hub. The hub is brighter than any single strand. The strands meet at shallow angles. They do not cross like sharp X shapes. They merge like braided currents that join into one deeper pool. Around the hub, the halo is round and thicker. The edge of the halo is smooth. It fades in a long tail of faint light. Another payoff arrives. Intersections are efficient builders. They collect material from multiple directions. They produce environments where galaxies can grow quickly. Now the section's second concept enters with careful breathing. Dark matter is mass that does not emit light. It can still shape gravity. It can still guide where a gas gathers. Two examples follow in plain imagery. A wind can shape dunes without being seen. A current can guide silt without being visible in the water's surface. In the same spirit, unseen mass can guide visible gas into filaments and nodes. The importance arrives in one sentence. The web can be more massive than what the light alone suggests. The limit of observation is stated softly and clearly. The brightest knots are easier to notice than the faint strands. The faint strands can sink into background noise. The edges of halos can fade below detectability. The true width of a filament can be larger than it appears. In addition, dark matter does not shine at all. Its presence must be inferred indirectly. The inference relies on patterns in where light appears. It relies on how structures cluster across the field. That method has a boundary. Different combinations of gas dust and age can mimic similar brightness. Another payoff settles. The web is known with confidence in outline, not in every fine thread. The scene widens into a calm map. Many knots appear across the field. Some knots sit alone. Others sit in small groups. Between groups, thin connections hint at filaments. The pattern resembles a loose mesh. It has gaps that look like voids. The voids are not truly empty, they are simply underdense. Their light is too faint to stand out. Their density contrast is low. Another payoff arrives. Emptiness in the sky can be a region where matter spreads thin, not where matter ends. The scale shift deepens again. A single knot can evolve into a galaxy. A group of knots can evolve into a cluster. The filaments between them can feed growth over billions of years. Time stretches as gently as space. A short phase of rapid assembly sits within a long era of slower inflow. The web is a conveyor of matter that runs quietly in the background. The analogy of drying mud returns with a new detail. As mud dries further, small cracks join larger cracks. The pattern becomes more connected. Some cracks widen, some fade. The final pattern preserves the history of stress. In the same calm way, the cosmic web preserves the history of early density variations. The present layout carries a memory of the initial conditions. Another payoff settles. Large-scale structure is a record written in geometry rather than text. The visual anchor lingers on a single filament again. Along the strand, a faint swell appears like a soft bulge. The bulge is not a separate object. It is a thickening of the same lane. Around it, a slightly brighter sheath forms. The sheath suggests warmer gas or more dust. The strand's edge remains diffuse. There is no hard boundary between filament and void. The transition is gradual. This physical softness matters. It shows that the web is not made of rigid lines. It is made of gradients. Those gradients guide matter without needing sharp walls. The section closes by letting the web become a stage for the next kind of evidence. If filaments feed knots, then sudden bright events can briefly light the surrounding medium. A transient flash can act like a moving lamp across dust and gas. The next movement follows those brief illuminations and keeps the web as the quiet background frame. A brief flare can leave a slow footprint across surrounding darkness. That footprint appears when a burst of light meets dust and returns in delayed layers. In that region, the burst itself is gone almost as soon as it arrives. What remains is geometry. A thin sheet of dust hangs like a veil in front of empty space. The veil is not uniform, it shows wisps and thicker knots. It shows a soft boundary where density rises. When the burst passes, the veil brightens for a moment. Then the brightness slips outward into a growing curve. The curve looks like a pale arc drawn on smoke. A first payoff settles. The fading burst still maps distance because scattered light arrives late from different paths. The main visual anchor forms as an expanding ring of glow on the dust sheet. The ring is not perfectly circular. It is slightly stretched. One side is brighter where dust is thicker. The inner edge is sharper than the outer edge. The outer edge dissolves into a faint haze. The ring grows larger over time. The dust itself does not move much on that timescale. The light pattern moves. Light behaves as a wave that can be redirected by grains. The grains do not need to shine by themselves. They only need to intercept the passing wave. A second payoff arrives. A moving ring on a still sheet separates the location of dust from the motion of the illumination. A definition comes quietly. A light echo is delayed, light scattered by dust. The echo is not a second burst. It is the first burst taking a longer route. Two examples follow in calm imagery. Sunlight slips through a small gap in clouds. A bright patch races across a lake surface. The gap closes and the patch vanishes. Yet mist above the lake can keep a faint glow for a moment. The glow lingers because light bounces many times before fading. The importance arrives in one sentence. A short event can reveal the shape of surrounding matter better than steady light can. The next checkpoint turns to the dust grains themselves. Dust is made of tiny solids. The grains scatter shorter waves more strongly than longer waves. That scattering changes the look of the echo. The inner edge can appear crisper in longer wavelengths. The outer halo can look wider in shorter wavelengths. A gradient appears along the ring. Brightness falls from the inner rim outward. The fall is not smooth everywhere. It breaks into patches where dust clumps. The clumps show sharper silhouettes. Each clump has a bright side facing the incoming wave. Each clump has a softer tail where scattered light diffuses. A small payoff settles. The echo does not only confirm that dust exists, it reveals dust as layers, clumps, and gradients rather than as a uniform fog. The section's main number arrives with a gentle scale shift. Over about 1 year, light travels about 1 light year, like the time winter ice forms and melts once. That timescale is small in cosmic terms. It is also large enough to watch a ring expand across a dust sheet. The ring's growth ties time to distance in a simple way. If the echo grows quickly, the scattering surface is closer. If it grows slowly, the surface is farther. Another payoff arrives. A changing pattern can turn a faint veil into a measured structure. A new visual anchor appears as a set of nested arcs. The first arc is tight and bright. A second arc sits farther out and dimmer. A third arc is barely visible and very broad. These arcs do not mean multiple dust sheets are required. They can form when dust is spread across depth. Light reaches near dust first. Later it reaches dust farther away along longer paths. The arcs are like shorelines seen at different tides. Each arc marks where the echo front intersects a layer of dust. Another payoff settles. The echo front acts like a moving slice through space. It reveals depth one thin layer at a time. The story then moves from appearance to mechanism. Scattering is redirection, not reflection, like a mirror. The grains are smaller than the wavelengths involved. The result is a preferential scatter that favours certain angles. More light can be sent forward than backward. That bias matters. It changes which dust layers are brightest in the echo. It also changes which parts of a ring stand out. A pale crescent can appear where the geometry favours scattering toward the observer's line of sight. A dim gap can appear where the geometry sends light elsewhere. Another payoff arrives. Brightness in an echo is a joint product of dust density and scattering angle. The limit of observation enters softly and precisely. The original burst cannot be watched again. its true peak brightness must be inferred. The dust distribution is not known in advance. Many different dust shapes can produce similar arcs when projected onto the sky. Resolution is limited at great distance. Fine ripples in the ring can blur into a smooth band. Faint outer halos can sink into background noise. The limit is clear. An echo can measure relative geometry well. It can struggle to deliver a single unique three-dimensional map without additional clues. Another gentle limit appears in timing. If measurements are sparse in time, the ring's growth can be sampled too coarsely. The ring can appear to jump rather than glide. The true smooth expansion is then reconstructed rather than seen. Another payoff settles. Even with limits, a moving echo adds a time dimension that steady images cannot provide. The section returns to the physical details of the dust sheet. The sheet shows a sharp edge where density rises. The echo ring brightens when it crosses that edge. The ring then dims as it moves into thinner regions. The edge acts like a contour line. It marks a transition in material. The ring's inner boundary remains crisp at the edge. The outer boundary stays feathered. A subtle shadow forms behind a dense knot. The shadow is not total darkness. It is a softened dim zone where fewer scattered paths remain. Another payoff arrives. Shadows inside an echo reveal occlusion and thickness, not merely absence. The scale shifts outward again. A single dense knot in the sheet can be small compared to the ring. The ring can be small compared to the host galaxy. The host galaxy can be small compared to the filamentary environment. Yet the same burst can illuminate all of these scales through time. First, the near dust brightens. Later, the more distant dust responds. The event becomes a quiet sweep through layers that span vast ranges. Light behaves as a probe that carries no tools. It carries only timing and direction. The final visual anchor slows on the outermost arc. It is faint and broad. It looks like a breath of light across a wide veil. The arc fades at the ends. It thins where the dust sheet breaks into wisps. It strengthens where the sheet thickens into a gentle ridge. The arc is calm. It is also informative. It shows that even in apparent emptiness, matter forms texture. The transition forward is soft. Once echoes sketch dust in broad strokes, finer structure can be traced in quieter regions. The next movement drifts into those dusty interiors, where layers and ridges shape what light can reveal. Inside a dusty region, the smallest changes in brightness can reveal hidden shape. The quiet meaning is that dust and gas form layered structure that controls where new stars can appear. In that region, darkness is not flat. It has texture. A broad veil stretches across the scene. Within the veil, thin ridges run like gentle waves. Between ridges, shallow troughs hold deeper shadow. The ridges are not sharp walls. They are gradients where density rises and falls. A faint glow leaks through the thinnest parts. The glow is warmer in tone. It is smoother than the surrounding darkness. A first payoff settles. When glow appears only in narrow lanes, the lanes mark where dust is thinner and gas is arranged. The main visual anchor becomes a face-on sheet of dust with parallel folds. The folds curve slowly. Each fold has a bright rim and a dim underside. The bright rim is not bright like a star. It is a slight lift in brightness. The dim underside is a soft shadow like a shallow hollow in a dune. The folds suggest compression. They suggest that gas is being pressed into layers. The physical detail is calm and specific. Each fold has an inner edge that looks sharper. Each fold has an outer edge that fades. Another payoff arrives. A sharper edge often indicates a denser boundary where material piles up. The first concept enters in a clean definition. Column density is the amount of matter along a line of sight. Higher column density means more dust and gas overlap. Lower column density means the view passes through less material. Two examples follow in plane imagery. A stack of thin curtains blocks more light than a single curtain. A shallow fog dims a distant lamp less than a thick fog. In the same spirit, a thicker column dims background light more strongly. The importance lands in one sentence. Mapping dimness across a sheet maps how matter is layered in depth. Another visual anchor appears as a narrow filament crossing the sheet. The filament is thinner than the folds. It looks like a drawn thread. Its center is darker than its edges. The edges show a faint glow as if the thread has a rim. The rim is caused by scattering and by a slight view into warmer material behind it. The filament bends gently. It does not kink. It meets a thicker knot where several faint threads converge. A small payoff settles. When several lanes converge into a knot, the knot is a likely site for denser gas. The second concept arrives with careful breathing. Shielding is protection from harsh radiation by surrounding material. When shielding is strong, molecules survive longer. When molecules survive, cooling becomes easier. When cooling becomes easier, gas can compress further. The idea stays simple. Dense layers block some light. Cooler interiors then form. A quiet, everyday analogy becomes the section's bridge. A loaf of bread cools from the outside inward. The crust cools first and dries. The interior stays warm longer. The interior also stays softer. The outside and inside are the same loaf. They feel different because the outside is exposed. The inside is shielded. In the same calm way, a dusty cloud has an exposed skin and a protected interior. Another payoff arrives. Protected interiors can host chemistry, and cooling that exposed skins cannot sustain. The loaf analogy guides attention to physical detail in the dust sheet. The exposed skin appears as a brighter rim in infrared. The rim is warmer. It forms a thin boundary around darker cores. Those cores are not empty. They are simply colder and more opaque. The boundary between rim and core is gradual, yet it can be traced as a contour of brightness. A third visual anchor appears as a pocket shaped like a rounded tear. The pocket has a curved edge. The edge is slightly brighter. Inside the pocket, brightness drops smoothly toward a darker center. The center has no point source. It is a calm depression in light. Another payoff settles. A smooth depression indicates a dense core that absorbs more background light. The scale shift arrives gently from grain to cloud. Dust grains are tiny, yet many grains together create a macroscopic shadow. A core can span light years. The skin around it can be a thin layer compared to its diameter. Still, that skin controls the interior. The number arrives softly and safely. A typical protected core can be about 1 light year across, like the distance light travels in a year of seasons. The comparison keeps it grounded. A year feels long in daily life. In space, a year of light is a small room within a vast hall. Another payoff arrives. A core that seems modest in size can still hold enough mass to form a cluster of stars. The limit of observation enters with clarity. Dust both reveals and hides. It reveals shape through shading. It hides true density by saturating at high column density. When a region becomes too opaque, additional dust does not make it much darker in the image. The darkest areas can all look equally dark. This is a measurement limit. It is not a lack of structure. It means the map can flatten the deepest valleys. Another limit follows in temperature. A warmer rim can mimic a thinner column. A cooler core can mimic a thicker column. Without multiple wavelengths, the two effects can be confused. The inference is indirect. Another payoff settles. Reliable structure maps require separating temperature from thickness, and that separation has boundaries at faintness. The section returns to the folds in the dust sheet. The folds resemble slow waves, but they are frozen in time at the moment of observation. The mind wants to see motion. It wants to see wind. In space pressure, waves and gravity can create layered density. The layers can persist for long spans. The folds can be set by converging flows. They can also be set by gentle compression from surrounding environments. The folds become a record. They preserve where gas has been squeezed. A visual anchor appears as a line of small bright specks embedded along one fold. The specks are not resolved into individual stars. They are compact warm spots. Each spot has a tiny halo. The halos overlap slightly. The fold beneath them is still visible as a ridge. Another payoff arrives. When warm spots appear along a ridge, the ridge is likely feeding localized heating, and heating often accompanies star formation. The fold, the core, and the filament now form one calm checkpoint chain. A filament carries material, a ridge collects it, a core shields it, a warm spot appears when collapse proceeds. This chain connects shape to process without forcing drama. The scale shift expands again. These structures sit inside a single galaxy. Many galaxies show similar patterns at different stages. Across the cosmic web, countless dusty sheets and filaments repeat. The repeated geometry suggests a universal set of rules. Matter cools when shielded, matter fragments when dense. Light traces the surfaces where dust warms. Another payoff settles. Large-scale evolution depends on small-scale layering because small-scale layering controls where stars can form. The closing returns to the darkest pocket. The pocket's boundary is smooth and curved. The rim is slightly brighter and warmer. The interior is quiet and deep. This calm interior sets the stage for the next movement. When two dense centers drift close, their surrounding gas and dust can merge and twist. The next section follows pairs of bright cores that share a common envelope and keeps the tone slow and steady. Two bright centers can share one quiet envelope before becoming one. The calm meaning is that gravity can bind separate systems and guide a slow inward drift. In that region, the sky shows a pair of compact glows. Each glow has a steep core. Each core is wrapped in a faint halo that fades outward. Between the two halos, a bridge of dim light connects them. The bridge is not uniform. It has a thicker middle and thinner ends. Along the bridge, a few small knots appear like gentle beads. At the outer sides, each halo shows a faint tidal tail. The tails are curved. They taper into the background and dissolve softly. A first payoff settles. A bridge and curved tails suggest interaction. They suggest that matter is being stretched and shared. The main visual anchor deepens into the bridge itself. It looks like a pale ribbon laid across darkness. The ribbon is slightly brighter near the centers. It dims in the middle, then brightens again where a knot sits. The ribbon's edges are feathered. There is no sharp boundary. On one side, the ribbon looks slightly thicker, like a shallow swell. That swell hints at a denser stream. The physical detail is calm and precise. The bridge has a gradient in brightness. It has a gentle curvature. It has small irregularities that indicate clumps of gas and stars. Another payoff arrives. Shared structure between two cores is evidence of a common gravitational field. A definition comes quietly. A merger is two galaxies becoming one bound system. The binding happens when gravity overcomes their relative motion. Two examples follow in plain imagery. Two drops on a window slide toward each other and share a thin trail. Two slow eddies in a pond drift together and form one broader swirl. The importance arrives in one sentence. Mergers can rapidly reshape galaxies and feed dense centers with fresh gas. The section's main analogy becomes a quiet dance of sand in shallow water. Two sandbars sit near each other. A slow current moves between them. As the current shifts, sand is pulled from one bar and laid onto the other. A narrow channel becomes a shared lane. Over time, the lane fills and the bars merge into one broader ridge. The process is not sudden. It is a gradual trading of material along a connecting bridge. Another payoff settles. In the same calm way, interacting galaxies exchange matter along tidal bridges before they blend. The next checkpoint turns to the mechanism that draws the pair inward. Dynamical friction is a gentle braking from gravitational wake. As a massive object moves through a sea of matter, it creates an overdense trailing region. The trailing region tugs back. The tug reduces orbital energy. The orbit shrinks. The term stays brief and clear. A definition fits within a single breath. Dynamical friction is a drag from gravity acting on a trailing wake. Two examples follow in plain imagery. A boat slows as it pushes water and leaves a wake behind. A heavy stone dragged through sand meets resistance from piled grains. The Y lands softly. Over long time, small braking can turn a wide orbit into a close embrace. Another visual anchor appears around the pair. The outer halos show faint asymmetry. One side of a halo is slightly stretched. The other side is more rounded. The stretched side points away from the partner like a tail pulled outward. The rounded side faces inward toward the bridge. The tail has a soft edge and a long taper. It fades into the dark field. This is a physical signature. It indicates tidal forces. Tidal forces are differences in gravity across an object. The nearer side feels a stronger pull than the farther side. The difference stretches matter. A payoff arrives. Stretching creates tails and bridges that reveal the direction of interaction. The section's main number enters with a gentle scale shift. The two bright cores can be separated by about 10,000 light-years, like two lanterns across a wide valley that would take ages to cross at a walking pace. The number is calm and round. It places the pair within one galaxy-size span. It also shows that merging begins long before any final union. At this separation, the bridge can already form. The tails can already lengthen. Another payoff settles. A merger is not a single moment. It is a long phase of shared gravity and exchanged matter. The bridge itself becomes a corridor for gas. Gas flows are not visible as streams. They are inferred from where dust warms and where knots appear. Along the bridge, slightly warmer patches can hint at compression. Compression can trigger new star formation. The patches are small, each has a faint halo. The halos overlap and blur. The bridge keeps its overall shape while the fine details remain uncertain. Another payoff arrives. Even without resolving every knot, the presence of knots along a bridge indicates that material is gathering, not merely being pulled thin. The limit of observation enters softly and precisely. At great distance, two close cores can blur into one if separation is below resolution. A single bright point can hide a pair. In addition, projection can mislead. Two objects aligned by chance can appear close, even if separated in depth. The bridge and tails help, but they can also be faint. If the bridge falls below the noise, the interaction can be missed. The limit is clear. Identification of mergers depends on seeing low surface brightness features, and those features are easiest to lose. Another payoff settles. The most telling parts of a merger are often the faintest parts. The story then moves inward to the centers. When two galaxies interact, gas can be driven toward the cores. Tidal torques can remove angular momentum from gas. The gas then sinks. Dense centers can brighten. Dust can thicken in partial rings around the cores. A visual anchor appears as a dim ring-like lane around one core. The lane is not perfectly circular. It is an oval. It has a sharper inner edge. Its outer edge fades into the halo. One side of the lane is darker where dust is thicker. The other side is lighter. Another payoff arrives. A dusty oval lane suggests gas being funneled inward along a rotating path. The scale shift becomes gentle and wide. The tidal tail extends tens of thousands of light years. The core region where gas piles up can be a small fraction of that, yet the tail is the source of future fuel. Matter pulled outward can later fall back. The interaction redistributes mass and then recollects it. The sandbar analogy returns in a new detail. A current first stretches a bar into a long ridge. Later eddies deposit sand back into a thicker mound. The cycle is slow. It changes shape without urgency. In the same calm way, a merger stretches galaxies into tails, then allows material to settle into a new form. Another payoff settles. The final galaxy that emerges can be larger and smoother, but it carries a memory in its outer faint features. The closing lingers on the pair again. The bridge remains as a quiet link. The tails remain as curved traces. The two cores remain distinct for now. The next movement follows the moment when gravity bends light itself. When mass grows and concentrates, background shapes can curve into arcs. That gentle bending offers another way to map hidden mass and scale. A distant shape can become clearer when it's gently curved. That clarity happens when gravity bends light and turns mass into a natural magnifier. In that region, a bright foreground glow sits near the center of the field. Around it, a thin arc of light appears. The arc is pale and smooth. It curves like a crescent moon, but without sharp tips. The arc has a brighter inner rim and a softer outer edge. Along the arc, brightness is not uniform. It rises into small beads, then relaxes into dim segments. Nearby, a second arc mirrors the first at a slightly different radius. The arcs do not look like separate objects by intent. They look like one distant source stretched into a ring-like trace. A first payoff settles. Curved arcs reveal mass that would otherwise be invisible because the bending depends on gravity rather than brightness. The main visual anchor becomes a partial ring around the foreground glow. The ring is incomplete. It breaks into two long segments. Each segment is thinner at the ends. Each segment thickens near the middle. The curvature is gentle and consistent. The ring's radius remains almost steady with small deviations. The deviations hint at uneven mass. A faint halo surrounds the foreground glow and blends into the background. Inside that halo, the ring is easiest to see. Outside, the ring fades. The physical details are calm and precise. There is a smooth curve. There are sharpness differences between inner and outer edges. There are bead-like bright spots along the curve. Another payoff arrives. The inner edge being sharper suggests that magnification compresses detail along one direction more than another. A definition comes quietly. Gravitational lensing is bending of light by mass. The light path curves because space is curved by gravity. Two examples follow in plain imagery. A clear glass bowl distorts the view of a pattern beneath it. A water ripple makes straight lines appear wavy on a pool floor. In the same spirit, mass distorts background light into arcs. The importance lands in one sentence. Lensing can amplify faint distant galaxies, allowing earlier structures to be studied. This section's main analogy becomes a calm piece of fabric pulled over a smooth pebble. A pattern printed on the fabric stretches near the pebble. Lines curve around the high point. The pattern becomes larger near the center of stretch. Farther away, the pattern returns to normal spacing. The pebble is not seen directly. Its presence is inferred by the distortion. Another payoff settles. The shape of a lens reveals the distribution of mass even when that mass does not glow. The next checkpoint turns to why arcs appear as arcs rather than as simple shifts. When a background source lies near perfect alignment behind a lens, the bending forms a ring. When alignment is less perfect, the ring breaks into arcs. The arc length depends on the closeness of alignment. The arc thickness depends on the size of the background source and the details of the lens. In that region, light behaves as if it has many possible paths. Some paths bend slightly, some bend more. The observer receives a composite. The result is stretched images. Another payoff arrives. A single distant galaxy can appear as multiple images, each carrying different magnifications of the same structure. The beads along the arc become meaningful. They indicate that the background source has internal clumps. When magnified, those clumps become visible as bright knots. The knots are not separate objects in the sky. They are features in the source. The lens stretches them along the curve. It compresses them across the curve. The inner rim looks sharper because the lens mapping is steep there. The outer edge looks softer because magnification changes more gradually outward. Another payoff settles. Edge sharpness in arcs is a signature of how rapidly bending changes with position. The section's main number arrives with a gentle scale shift. The ring radius can be about 1 arc-second, like the apparent size of a small coin, seen from several kilometers away. The comparison keeps it grounded. It shows that dramatic cosmic magnification can occur within a tiny angle. The arc-second scale feels small, yet it encodes mass on scales of tens of thousands of light-years. Another payoff arrives. A tiny curve on the sky can imply a vast lens structure in space. The story then moves from appearance to measurement. The ring radius sets a rough mass scale. Larger radius implies stronger bending. Stronger bending implies more enclosed mass. The exact conversion depends on distances. Distances are inferred from redshift. Redshift connects back to earlier sections. In that region, a signal would carry both a color shift and a spatial curve. The combined clues allow mass and distance to be separated. Another payoff settles. Lensing links geometry to expansion because distance relationships shape the bending strength. The limit of observation enters softly and precisely. Lensing magnifies, but it also distorts. It can stretch a compact clump into a long smear. It can overlap different parts of the source along the arc. It can create multiple images that blend when resolution is limited. The lens itself can have substructure. Small clumps of mass in the lens can create extra wiggles in the arc. Those wiggles can be mistaken for structure in the source. The limit is clear. Interpreting arcs requires a model of the lens mass distribution, and different models can fit the same arc within uncertainty. Another payoff settles. The arc is a constraint, not a complete map, and careful inference is needed to avoid overconfidence. A second limit appears in faintness. The outer parts of the ring are low surface brightness. They can sink into the background. If only the brightest arc segments are seen, the lens model becomes less constrained. The missing segments matter. They carry information about the lens symmetry. Without them, mass estimates broaden. Another payoff arrives. The most informative parts of a lens are sometimes the dim segments that are hardest to detect. The visual anchor returns to the incomplete ring. The broken segments are not symmetric. One arc is longer, one is shorter. The longer arc has more beads. The shorter arc has a smoother glow. This asymmetry can come from the lens shape. It can also come from the background source shape. The pattern invites a calm disentangling. If the lens mass is elongated, arcs tend to form at preferred angles. If the source is elongated, its magnified image can be longer on one side. Another payoff settles. Lensing turns a single observation into a puzzle of geometry, where curvature and brightness together carry the solution. The scale shift widens again. The arc-second ring is tiny on the sky. The lensing mass is a galaxy or a group of galaxies. Behind it lies a source from early cosmic time. Between them lies expanding space. The path of the light crosses billions of light years, yet the bending occurs mostly near the lens. A small region along the path controls the apparent shape. Another payoff arrives. A local concentration of mass can alter the appearance of the entire distant universe behind it. The section closes by letting lensing become a tool for the next theme. When early galaxies appear too compact or too bright, lensing can be a helpful check. It can reveal that some objects are magnified. It can also show that some objects are genuinely dense. The next movement follows compact galaxies that remain compact even after lensing is accounted for and keeps the tone soft and steady. A compact galaxy can look like a single calm ember, yet it can hide a long story at its edge. The quiet meaning is that early galaxies can pack light into small volumes, then grow broader without adding the same kind of light. At this distance, a small oval appears with a steep centre. The centre brightens quickly, then levels into a rounded peak. The outer light falls off in a smooth slope. The slope is not uniform. It shows a faint shoulder where brightness drops faster for a short span. Beyond that shoulder, a thin haze continues. The haze is delicate and wide. It fades into the background without a sharp boundary. A first payoff settles. A galaxy can have two sizes at once. A bright inner size defined by strong light, and a larger faint size defined by barely visible outskirts. The main visual anchor holds on the brightness profile like a quiet landscape. The core is a small hill with a steep face. The shoulder is a gentle ledge. The outer haze is a long plane that slopes toward darkness. Along the plane, tiny ripples appear as mild fluctuations. Those ripples are not noise alone, they can be the imprint of real structure. The physical detail is calm and specific. The inner edge looks crisp. The outer edge looks like mist with no true border. Another payoff arrives. When the edge's misty size becomes a matter of definition rather than a single fact. A definition comes softly. Effective radius encloses half the emitted light. The phrase stays simple. It is a way to measure size without needing a hard edge. Two examples follow in plain imagery. A pond can be judged by its deep centre. It can also be judged by its shallow shoreline. Both are part of the same water body. A cloud can be judged by its dense core. It can also be judged by its faint wisps. Both belong to one formation. The importance lands in one sentence. When size is defined consistently, compactness can be compared across time. The section's main number arrives with a gentle scale shift. Some early compact galaxies have an effective radius of about 1,000 light-years, like the distance light travels in 1,000 years. The number feels quiet, yet it is small for a galaxy. It means a large fraction of light sits in a tight region. At this distance, light behaves as a compressed signal. Many stars contribute, but the glow remains confined. A payoff settles. Compactness is not only about mass, it is about how quickly brightness falls with radius. The story then moves to how compactness changes. A compact glow does not always remain compact. Over long time, outer regions can grow brighter. The core can become less dominant. The brightness profile can flatten. The shoulder can move outward. The haze can thicken into a broader envelope. A new everyday analogy becomes the bridge. A fern frond begins tightly curled. Over time it unfurls into a wider arc. The total material is similar. The shape changes because tension and stiffness relax. In the same calm way, a galaxy can broaden as orbits spread. Another payoff arrives. Growth in size can happen even when the inner light stays steady, because the outer light becomes easier to see. The visual anchor shifts to a second compact galaxy. This one has a sharper rim in its inner region. The rim looks like a contour where brightness drops abruptly. Outside the rim, a faint ring-like trace appears. The trace is not a perfect circle. It is an oval with a slightly brighter arc on one side. The oval trace suggests a subtle shell. Shells can form when material is added in discrete episodes. They can also form when orbits settle into layered structures. The physical detail remains gentle. The shell is faint. Its edge is slightly sharper than the surrounding haze. Another payoff settles. Faint shells suggest that growth can occur by adding outskirts, not by inflating the core. The next checkpoint brings in a second concept with quiet clarity. Minor mergers are small additions of mass over time. The additions do not dominate the central light. They tend to deposit stars into wider orbits. The central profile can stay steep. The outer envelope can thicken. Two examples follow in natural imagery. A river delta grows by many small deposits. The river mouth stays in place, yet the shoreline advances. A snowdrift grows by repeated lightfalls. The dense base remains, yet the outer slope extends. The importance lands in one sentence. Repeated small additions can make a compact galaxy appear less compact without rewriting the core. Another visual anchor appears in the outskirts. The outer haze shows a mild asymmetry. One side extends farther like a faint tail. The tail is not bright. It is a diffuse wing that tapers slowly. Along the wing, brightness shows a gradient that becomes smoother outward. This gradient implies a mix of older stars and scattered dust. The wing suggests that the galaxy is not perfectly settled. It still bears traces of added material. Another payoff arrives. When the outskirts are uneven, growth is still active even if the core looks stable. The scale shift widens from inner to outer. The inner 1,000 light-years hold half the light. The outer tens of thousands of light-years can hold a large share of mass that is faint. The faintness is not absence. It is a change in surface brightness. Surface brightness is light spread over a patch of sky. Spread the same light wider, and it looks dimmer. A payoff settles. A galaxy can grow in area faster than it grows in total light, making edges disappear into darkness. The limit of observation enters softly and precisely. At great distance, faint outer envelopes fall below detectability. The measured size then shrinks. The effective radius can appear smaller because the outskirts are missed. In addition, dust can hide light in some bands. Young stars can brighten a core and bias size inward. Lensing can stretch shapes and alter apparent radii. The limit is clear. Size is inferred from light that survives faintness and filtering, and some light does not survive. Another payoff arrives. A compact galaxy can be truly compact, yet it can also be a partial view of a larger structure. The visual anchor returns to the profile as a calm slope. Imagine the same galaxy seen deeper. The plane of the outer haze extends. The ledge becomes less prominent. The mist begins to show subtle ripples that were invisible before. The ripples are like low dunes on a long flat. They do not change the core. They change the sense of total extent. Another payoff settles. Deeper visibility does not add new objects. It reveals old outskirts that were always there, which changes the perceived scale. The fern analogy returns in a new detail. As the frond unfurls, the tight curl remains a memory at the base. The wider arc becomes the dominant shape from a distance. In the same calm way, a compact core can remain while the envelope grows, and the overall galaxy looks different with time. The section closes by widening to consequence. If sizes evolve, then comparisons across epochs require careful distance calibration. Distances set physical scales. Distances also set how surface brightness fades with expansion. The next movement follows two distance ladders that aim to measure expansion and keeps the tone gentle and steady. A nearly uniform glow can carry a hidden yardstick across the entire sky. The quiet meaning is that expansion can be constrained by comparing an ancient fixed scale to later light that changes with distance. At this distance, the scene begins as a soft shell of background light that fills all directions. The shell looks smooth at first, then faint mottling appears. The mottling is gentle. It forms tiny patches that are slightly brighter or dimmer. The patches do not make sharp borders. They blend into one another like slow weather in a thin haze. A first payoff settles. A weak ripple pattern can act as a remembered scale because its preferred spacing is set early and carried forward. The main visual anchor holds on that shell. The mottling is not random speckle. It has a characteristic grain. Some patches cluster at similar angular sizes. Between clusters, the pattern relaxes. The shell feels like a calm surface with subtle texture. The texture does not move quickly. It is a frozen imprint from a young phase of the universe. The physical detail is quiet but clear. The mottling has gradients rather than edges. It has soft boundaries rather than lines. Another payoff arrives. A soft pattern can still be measured in principle because the preferred scale repeats many times across the sky. The first concept enters with a clean definition. Redshift is stretching of light to longer wavelengths by expansion. In plain terms, a wave leaving a distant source arrives stretched. The colour shifts toward longer waves. The shift increases with distance in an expanding universe. The Y lands in one sentence. Redshift turns light into a gentle clock that encodes how much space has expanded along the path. A second visual anchor forms as a distant galaxy whose light is reddened and faint. Its core is compact. Its outer glow fades into darkness. The edges are soft. The colour is warmer than nearby sources. The warmth is not heat in the object. It is the stretching of the wave. A small payoff settles. A redder spectrum implies a longer journey through expansion, even when the object itself is not intrinsically red. The section then moves to the idea of a fixed scale. A definition comes softly. A standard ruler is a known physical size imprinted in matter. The imprint forms early. It then expands with the universe. Two examples follow in calm, natural imagery. Waves on a beach leave parallel ridges in sand as the water retreats. The ridges keep a characteristic spacing even as the shoreline shifts. In a similar spirit, early pressure waves leave a characteristic spacing in the distribution of matter. The importance arrives in one sentence. If the ruler size is known, its apparent size reveals distance and expansion. The main number enters with a gentle scale shift. The ancient shell of background light decouples about 380,000 years after the beginning, like the first moments of cooling after a very long heating phase. The comparison is meant to settle the sense of timing. The universe is still young, yet it is already structured enough to carry a stable imprint forward. Another payoff arrives. A feature set in the first few 100,000 years can constrain behaviour over billions of years, because the imprint becomes a reference carried by expansion itself. The section's primary analogy becomes a glacier. A glacier builds layers as snowfall compresses over time. Each layer has a subtle boundary. The boundaries are not sharp lines. They are gradients in density and grain size. As the glacier flows, the layers stretch and curve. The layers still preserve a record of conditions at formation. In the same calm way, early imprints in the universe stretch with expansion. The imprint does not need to stay rigid. It needs to stay recognizable as a preferred scale in the pattern. Another payoff settles. A ruler in cosmology can be a pattern in the material, not a rigid object. The next checkpoint turns to the later, more local ladder of distance. A definition comes quietly. A standard candle has a predictable luminosity. If luminosity is known, apparent brightness reveals distance. Two examples follow in plain imagery. A steady bioluminescent glow in deep water looks dimmer with more water between it and the surface. A fixed phosphorescent patch on rock looks fainter when seen through thicker mist. The importance lands in one sentence. Predictable light sources allow distances to be inferred without relying on the ancient pattern alone. A visual anchor appears as a bright transient flare in a distant galaxy. The flare rises and fades. The light curve is smooth. Its peak is broad rather than spiky. The glow leaves a faint halo in surrounding dust, then the halo fades. The physical detail is gentle and specific. The flare has a rounded crest. The fading tail is long and smooth. A small payoff settles. The shape of a flare over time can help classify it as a predictable event, which strengthens its use as a distance marker. The scale shift becomes layered. On one side, the ancient shell sets a ruler across the largest volumes. On the other, predictable sources set steps across nearer to farther galaxies. Both approaches meet in a shared region where both can be applied. Agreement tightens the expansion story. Disagreement highlights missing pieces. Another payoff arrives. Two distance paths can reveal the same expansion in different ways, which makes tension informative rather than merely confusing. The limit of observation enters softly and precisely. The ancient ruler depends on assumptions about early conditions. Small changes in composition and temperature history can shift the inferred ruler length. The inference is indirect. It relies on models that translate pattern spacing into physical scale. The local candle path has a different limit. Predictable sources can still vary. Dusk can dim and redden them. Environments can change their peak brightness. Selection effects can favor brighter events at great distances. The limit is clear. Both ladders can be biased without obvious warning because the missing information hides in faintness and in model dependence. Another payoff settles. The safest constraints come from cross-checks where different systematics fail in different ways. The visual anchor returns to the mottled shell. Imagine the mottling as a calm field of gentle hills. The hills have a characteristic spacing. That spacing becomes a ruler laid across the sky. Now imagine later matter as a sparse foam. The foam has preferred separations that echo the ancient spacing but stretched by expansion. The echo's faint. It is not a sharp lattice. It is a statistical preference. Another payoff arrives. A ruler can survive as a tendency rather than as a visible grid which allows it to persist through complex growth. The glacier analogy returns with one more detail. Deep layers compress. Shallow layers remain looser. Flow bends layers around obstacles. Yet the layering remains traceable in cross-section. In the same way, later structure growth bends and amplifies patterns. The underlying scale can remain traceable, even as details become nonlinear. The section closes with a soft widening. Expansion is not only a measure of distance, it sets how quickly time unfolds across cosmic history. It sets how horizons grow and how light from early eras reaches later eras. The next movement drifts from rulers and candles toward the long sweep of time itself, and the way expansion shapes what can ever be observed. The farthest edge of the visible universe is not a wall of matter but a limit of arrival. That limit exists because light takes time and expansion changes the distance while the light travels. In that region, the sky can be imagined as a deep bowl of darkness sprinkled with faint points. The points thin out toward the deepest distances. The thinning is not only emptiness, it is also a boundary set by time. A small payoff settles. Visibility ends where signals have not yet had enough time to reach the present. The main visual anchor forms as a slow wavefront in a still foggy valley. The fog is uniform at first. Then a faint brightening spreads in a wide arc. The arc is the leading edge of a distant flash diffusing through the mist. The edge is not sharp. It is a gradient that rises, peaks and fades. Behind the edge, the valley is softly illuminated. Ahead of the edge, the valley remains unchanged. The physical detail is gentle and clear. The edge has thickness. It has a smooth boundary. It has a layered fade rather than a line. Another payoff arrives. A moving edge with thickness makes a clean point. Information is not everywhere at once, even in a vast connected space. A definition comes quietly. Look-back time is the time light spends travelling to the present. It is not a special kind of time. It is ordinary time carried by a wave across expanding space. Two examples follow in calm imagery. A distant thunderhead glows, and the glow arrives later than the change within the cloud. A far-off ridge catches sunlight, and the glow of the ridge reaches other valleys after a delay. The importance lands in one sentence. Looking far away means seeing earlier states because the light begins its journey long ago. A small payoff settles. Distance becomes a way to read history without needing memory. The next checkpoint introduces the horizon that belongs to the past. A definition comes softly. The particle horizon is the farthest distance from which any signal can have arrived. It is a limit set by the age of the universe and by expansion. The idea stays plain. A region beyond that boundary can exist, but it has not yet influenced the present with light. The visual anchor returns to the foggy valley. The brightening edge expands outward. Its radius grows steadily. The center remains softly lit. The edge becomes fainter as it spreads. Yet the edge still separates what has been reached from what has not been reached. Another payoff arrives. A horizon is not a place where space ends. It is a place where contact has not yet occurred. The section's main number arrives with a gentle scale shift. The universe is about 14 billion years old, like 14 billion slow turns of a season wheel that never stops. The number is calm and round. It grounds the horizon in time rather than in mystery. A wave can only travel for about 14 billion years since the earliest eras. Expansion also stretches the route. That stretching allows the visible volume to be larger than a simple time times speed would suggest. Another payoff settles. The visible universe can be huge even when its age is finite, because expansion changes the map while the journey unfolds. The section's main analogy becomes rings in a calm limestone cave. Water drips from a ceiling crack over long time. Each drip leaves a faint deposit. The deposit forms a thin ring where water spreads before drying. Over many cycles, rings build into a layered collar. The collar's outer rim marks how far water reaches in most drips. The rim is not a hard edge. It is a zone where deposits thin out. In the same calm way, repeated wave arrivals build a record within the reachable region. The outer rim is where reach becomes sparse. Another payoff arrives. A boundary can be traced statistically, even when no single object marks it. The next checkpoint turns to a different horizon that belongs to the future. A definition comes quietly. The event horizon is the boundary beyond which signals sent now will never arrive. The reason is accelerated expansion. Space between regions can grow so quickly that light cannot close the gap. The idea remains gentle. The future can include regions that recede out of causal contact even while they continue to exist. A visual anchor appears as two patches of dandelion seeds drifting apart in still air. The seeds begin close. A broad invisible current then carries the patches away from each other. The separation grows. Each patch remains cohesive inside itself. The gap between patches widens faster than the seeds drift back. Another payoff settles. A separation can become permanent without any barrier simply because the background flow keeps increasing the distance. The physical detail returns to the idea of edges and gradients. A horizon in an accelerating universe is not visible as a line in the sky. It is expressed in how light from very distant sources fades and reddens. It is expressed in how time dilation stretches transient events. It is expressed in how the background between structures looks increasingly empty. Light behaves as a messenger that must pay the cost of expansion. The cost appears as stretched wavelengths and reduced surface brightness. Another payoff arrives. Expansion does not only shift colors, it can also erase detail by spreading light thinner across larger apparent areas. The limit of observation enters softly and precisely. The earliest visible light in certain bands comes from a time after the universe becomes transparent to those wavelengths. Before that, scattering is strong and the view is opaque. This is a physics limit, not a weakness of vision. Another limit follows from faintness. At extreme distances, surface brightness drops. Extended halos sink into noise. Only compact bright regions remain detectable. The horizon is then approached not as a crisp boundary, but as a zone where only certain kinds of objects are seen. A third limit is model dependence. Converting redshift to distance requires an expansion history. Different histories shift inferred distances in subtle ways. Another payoff settles. The farthest reach is not read directly from one image. It is inferred from light models and the physics of transparency. The story then gathers the scale shift into a single calm picture. In nearby space, a compact galaxy shows a core and a faint envelope. Farther out, similar envelopes fade and only cores remain. Farther still, even cores are rare, and the background dominates. Beyond the particle horizon, signals have not arrived. Beyond the event horizon, future signals will not arrive. The cave ring analogy returns with one more detail. Deeper in the cave, drips are rarer, and deposits are thinner. The outer ring becomes patchy. The collar still exists, but it is harder to trace. In the same way, horizons are traced by patterns and scarcity, not by walls. Another payoff arrives. The universe carries two gentle edges at once, one set by past arrival, and one set by future departure. The closing slows to the foggy valley again. The brightening edge becomes faint as it expands. The valley behind it is softly lit. The valley ahead stays unchanged. The scene feels restful because nothing forces a sudden stop. The next movement widens into the far future. It follows how expansion shapes what remains visible, and how the sky slowly simplifies into quieter light. Even the widest cosmos can become calmer when distance grows faster than light can keep up. Accelerated expansion slowly separates bound islands of matter and thins the background glow into an ever softer haze. In that region, a single large galaxy sits inside a broad halo. The halo is faint and rounded. Its brightness falls with a smooth gradient. The inner glow is steady. The outer edge is not a line. It is a long fade that becomes indistinguishable from darkness. Nearby, a few smaller companions linger as dim ovals. Farther out, the field holds fewer points. The emptiness is not a wall. It is the effect of separation and time. A small payoff settles. The visible universe can feel smaller in practice, even while space grows larger in total. The main visual anchor stays with a halo's edge. The edge looks like mist on cold water. It has layers. It has a subtle shoulder where the fade steepens. Beyond the shoulder, the glow continues as a thin veil. The veil is barely there. It is a boundary made of faintness rather than matter. Light behaves as a messenger that grows tired without losing speed. The tiredness comes from stretching. The same count of waves arrives, but each wave carries less energy. Another payoff arrives. Dimming with distance is not only about travel time, it is also about the stretching of the wave itself. A definition enters quietly. Dark energy is persistent pressure that drives expansion faster. The term stays contained. Two examples follow in calm natural imagery. A river current can strengthen downstream and widen the gap between drifting leaves. A rising warm air layer can lift thin clouds so they spread and separate. The importance lands in one sentence. Faster expansion increases the separation between distant regions faster than signals can bridge. The next checkpoint turns that idea into a boundary. Cosmic event horizon is a boundary beyond which signals never arrive. The definition is short and clean. The boundary is not a surface. It is a consequence of the future. If accelerated expansion continues, distant regions recede so quickly that light sent later can never catch them. A payoff settles. Some separations become permanent without any barrier, because the background growth never relaxes. The visual anchor widens. Beyond the halo, the space between galaxies is not empty of all things. A very faint background remains. It is a smooth glow with almost no structure. Its wavelength grows longer with time, its intensity drops as it spreads. The glow becomes more like a gentle swell than a visible texture. The swell has no sharp crests. It has slow undulations. It is present, but increasingly quiet. Another payoff arrives. A background can persist while becoming practically featureless, because stretching erases contrast as well as energy. The section's main analogy becomes a drop of dye in an open ocean. The dye begins as a visible cloud. The cloud spreads. Currents stretch it into long filaments. The filaments thin into a wide faint tint. The tint remains in the water, yet it stops standing out. In the same calm way, ancient radiation spreads through expanding space. The wave remains, yet its ability to mark a pattern fades. Another payoff settles. A signal can still exist while losing the power to make a measurable imprint on its surroundings. The story then shifts from the present into a quiet future. In about 100 billion years, like many billions of revolutions of a small world around its star, the separation between distant galaxies grows vast. Some galaxies remain bound in local groups, others drift away beyond reach. The count is not meant to feel sharp. It is a round marker of long time. It marks an era when most distant structures no longer share light with this region. Another payoff arrives. The future sky can simplify, because the horizon of contact can shrink relative to the growing total volume. The main visual anchor returns to the halo edge again. The faint veil around the central galaxy remains. The companions remain nearby. Yet beyond them, fewer and fewer external lights arrive. The darkness is not sudden. It thickens like a slow dusk. The transition is gentle because it is driven by geometry, not by a single event. The physical detail stays in the gradient. Each decade of radius holds less brightness. The edge becomes smoother. The contrast between core and outskirts grows. Another payoff settles. Isolation is visible as a change in gradients, not as a hard cutoff. The scale shift continues inward. Inside the bound island, gravity still gathers matter. Orbits remain, halos remain. Gas can cool and form new stars for a time. The internal evolution is local. It does not require contact with the rest of the universe. Yet the external context fades. The bound island becomes a self-contained chapter. Another payoff arrives. Local physics continues, but the global map becomes harder to read because fewer external references remain. The limit of observation enters softly and precisely. Beyond the event horizon, no new information can arrive. The present cannot be influenced by light that is emitted after the boundary becomes effective. Even within the reachable region, the background glow stretches to longer wavelengths. When the wavelength becomes longer than the size of a typical atom, absorption becomes unlikely. Interactions with ordinary matter become rare. The signal persists, yet it becomes harder for matter to register. The limit is clear. A fading background can become physically inaccessible as an interacting influence, not only as a faint image. Another payoff settles. Some knowledge fades not because it is forgotten, but because the universe stops delivering it in an interactive form. A second limit follows from inference. When distant galaxies disappear beyond reach, the expansion, history outside the bound island becomes less constrained by fresh signals. The local region retains clues from earlier eras, but those clues age. They redshift, they dilute, they stop offering new cross-checks. The bound island can remain luminous, while the wider universe becomes a silent context. Another payoff arrives. A quieting sky reduces the number of independent tests available, even if internal structure remains rich. The ocean dye analogy returns with a new detail. The last visible tint is not uniform. It forms broad bands. Some bands are slightly darker, some are slightly lighter. The pattern is smooth. The pattern is large scale. Yet as time passes, even those bands blend into a nearly uniform colour. In the same way, the last traces of background structure become smooth. They persist statistically, but they stop providing sharp landmarks. Another payoff settles. The universe can move towards simplicity by smoothing differences rather than by removing substance. The closing holds a calm frame. The central galaxy remains wrapped in its halo. The halo's edge remains a soft fade. The surrounding emptiness deepens without a boundary. The future does not snap shut. It slowly grows quiet. The next movement follows what this quiet means for long-time scales of matter and energy, and keeps the tone gentle and steady. A universe can keep expanding and still grow quieter in the ways it can rearrange itself. Over immense time, usable contrast thins as energy spreads, and light stretches into longer waves. In a dark region between galaxies, a faint arc crosses the field like a pale ribbon. The ribbon is a tidal stream of stars. It curves in a slow S shape. Its center line is slightly brighter than its edges. The edges feather outward into a gentle gradient. Along the arc, small knots appear where the density rises. Between the knots, the stream is smooth and fine. A soft, shadowy lane runs beside part of the ribbon where thin dust dims the glow. This is how structure shows a boundary without a wall. The arc is not static. Each star follows an orbit set by gravity. Streams like this begin when two galaxies pass close enough for tidal forces to matter. A smaller system is pulled unevenly. Stars on the near side feel a slightly stronger tug than stars on the far side. Some stars drift ahead along the orbit. Some lag behind. Two arms form one leading and one trailing. Over time, the arms wrap into long arcs that can span a vast fraction of the host's surroundings. As time passes, tiny differences in speed spread the stars along the path. The knots blur, the sharpness softens. The ribbon becomes longer and thinner. Order can unravel by slow stretching, not by sudden disruption. One idea holds the pattern in a single phrase. Entropy measures how spread out energy becomes. When energy is concentrated, differences can drive change. When energy is spread, thin change becomes harder to sustain. Two examples keep the idea grounded in simple physics. A warm pocket inside a deep layer of rock shares heat with cooler layers. Over time, the temperature gradient flattens into near uniformity. A swirl of warm gas inside a cold cloud mixes into its surroundings. The swirl loses its sharp boundary and becomes a faint tint. In a growing cosmos, many processes drift towards smoother, more uniform states. The stellar stream shows this drift in a visible shape. The dust lane beside it is not thick. It is a thin veil with a darker spine and lighter edges. As the stream stretches, the veil spreads too. The darker spine becomes harder to trace. The lighter edges merge into background darkness. Entropy is the fading of contrast in real shapes, not only an abstract rule. Another quiet idea describes what happens to light itself. Redshift stretches light to longer wavelengths as space expands. The stretching lowers the energy carried by each wave of light. A glow that begins crisp becomes softer in character with distance and time. Some light slides out of the range where it interacts strongly with ordinary matter. It still travels. It simply couples less to the particles and dust it passes. Old light is not erased. It becomes harder for that light to warm ionize or sculpt what it crosses. The scene widens outward in scale. Between galaxies, the background is not perfectly black. A very faint bath of ancient radiation remains. It is almost uniform. Its tiny variations smooth as long waves grow longer. The field resembles a surface of dark water under calm air. There are swells so broad that crests are barely distinct. At the larger scales, difference survives mainly as extremely soft texture. With expansion, the typical wavelength of that background grows and grows. What starts as a short wave becomes a long, gentle swell. The energy per wave falls as the crests spread apart. Heating and cooling still occur locally, yet the grand background becomes increasingly quiet. Time now shifts by orders of magnitude. Over about 100 trillion years, like roughly 7,000 times the universe's present-age new bright stars become extremely rare. The phrase describes an era rather than a single threshold. Gas that can cool and condense is mostly used dispersed or locked into faint remnants. Small, long-lived stars continue shining far beyond that era. Yet the average sky gains fewer fresh sources of high-energy light. Dimming comes from the slowing of renewal as much as from the fading of old sources. In a wide dune field under steady wind, sharp crests and deep troughs appear at first. Grains slide down lee slopes in thin sheets. Wind shear lifts only the finest grains into a pale haze that settles elsewhere. Over long time the dunes spread and flatten. Crests round off. Shadows shorten. Ripples lose their crisp edges and become low-relief waves. The landscape remains, but contrast is reduced. In the same calm way, cosmic structures can persist while their sharpness fades. Quiet change is often a smoothing of gradients rather than a loss of everything. Limits appear where intuition reaches too far. The far future cannot be observed directly from the present. It is inferred by extending present laws forward in time. That inference relies on assumptions about how expansion behaves over enormous spans. It also relies on how matter continues to interact with faint, stretched radiation. Another limit comes from horizons. In an accelerating expansion, regions can slip beyond contact so no new signals ever arrive from them. Even within the reachable region, stretched light can become so low in energy that absorption and scattering grow rare. The limit is not only distance, it is the weakening of interaction itself. Over even longer spans, collisions between stray particles become rare events. Long-lived remnants cool and fade toward the background. Light continues to cross the void, but it carries less ability to trigger new structure. The stellar stream returns one last time as a quiet landmark. The S-shaped arc still spans the dark. The brightest knots are less distinct. The dust shadow beside it is thinner and more uniform. The stream's edges look more like fog than like thread. Its gradient is smooth enough that the boundary becomes a matter of definition. Near the centre of the arc, a slight ridge remains where the density is highest. Farther out the ridge dissolves into a wide faint band. The long-term direction is toward broader, softer features that blend into silence without ever forming a wall. The closing turns gently toward the last chapter. After the future becomes quiet in light and contrast, the remaining story is mostly about stability and stillness. The next section eases that stillness into a soft landing without urgency and without strain. Darkness near the end of the cosmos has texture. It is filled with old light that is stretched and thinned by expansion. At this distance, a dust grain drifts through a cold fog of photons. Each photon carries a different past. Some come from a star that has already cooled. Some come from a galaxy that has blurred into a faint smear. The grain offers one hard surface. A photon skims it and scatters. Then it continues into a wider emptiness. One thing becomes clear here. Light does not need fresh sources to persist. It only needs room to travel. The scene widens until single sources stop standing out. A distant galaxy becomes a dim disk with a brighter center. Its rim fades by a soft gradient instead of a crisp edge. Dark lanes turn into gentle shading across the face. In that wash of light, redshift is light stretched into longer waves. A ripple that starts tight becomes spread out. A color that starts warm becomes colder. Brightness also thins because the same light is shared by more space. Another detail becomes clear. Distance is not only far away. Distance rewrites what a glow can be. In the near field, a beam paints a clear line. Farther out, the same beam becomes a wide cone with a fading edge. At greater stretches, a wave can grow so long that it slides past small grains with little scattering. The glow then feels less like rays and more like a quiet pressure that barely warms anything. Even the idea of a sharp shadow changes. Against a nearly uniform background, a remnant makes a soft silhouette. Its outline is not hard. It is a dimming that blends back into the glow. A quieter limit matters more than any blurred rim. A cosmic horizon is the farthest light can ever reach. It forms when the gap between regions grows faster than light can cross. It resembles ice forming on a still lake at night. The first skin appears near the shore. The open water remains in the centre. Yet the rim keeps advancing as cooling spreads. Why this matters becomes clear at once. An object can keep shining and still slip beyond reach. Nothing blocks it. The path itself lengthens too fast. A last flash can be emitted and never be received anywhere else. The lake image holds steady as the cosmos changes around it. On the ice, a faint milky band forms where new crystals knit together. The band marks the moving boundary without noise. In the sky, an analogous band exists in time. There is a last moment when light from a region can still arrive. After that moment, only older light remains. It keeps reddening as it travels. Inside the reachable region, the remaining radiation keeps evolving. Photons become rarer per volume as space expands. Their wavelengths lengthen, so each carries less heat-like effect. Separate beams overlap until direction loses meaning. The background turns smoother because waves mix and blur. A faint pattern still remains. It appears as tiny ripples of brightness laid over a near-even glow. Those ripples carry a quiet clue. They preserve the memory of earlier structure in low contrast. The ripples are not a map of current objects. They are a trace of old clumping, smeared by time and stretched by expansion. Another slow scene settles in. A dark remnant drifts across that glow and leaves a slow-moving notch. The notch is shallow. It fades as the remnant moves on. A gentle scale shift carries the story from grains to ages. After about 1 trillion years, the cosmos has time to simplify again and again like mountains wearing down into low plains under steady wind and rain. Fast-burning stars are long gone. Only slow ones persist, and they shine dim and red. Even that dim light is stretched further as it travels. More and more of what remains is not starlight at all. It is afterglow from earlier eras cooled by endless stretching. Another truth settles in. A late universe is not a stage for bright events. It is a reservoir where faint radiation spreads toward uniformity. Local gravity still holds some matter together. Within those bound pockets, orbits continue and settle. Gas becomes scarce. Encounters become rare. When a rare collision does happen, it can release a photon. That photon joins the background and is stretched again. Over time, the background acts like a gentle bath. It smooths contrasts by being everywhere at once. Limits of intuition appear, and they have names. The horizon blocks information from beyond it. A signal cannot arrive from a place that recedes too quickly. Inside the horizon, the faint background also sets a second limit. When contrasts fall below the natural jitter of the field, detail cannot be separated. This limit does not soften with time. It is a consequence of weak signals and finite resolution in nature. Some long-term physics also stays uncertain. Matter may remain stable for extreme durations, or it may slowly decay into lighter remnants. Either way, the late sky tends toward the same mood. Cold light drifts, structure relaxes, contrast fades, the lake returns. The ice sheet grows until no open water remains. Hairline cracks lace the surface. The cracks do not widen into drama, they simply mark where the sheet adjusts as it cools. In the cosmos, the afterglow spreads until it dominates the scene. It has no bright center. It has no sharp border. It is a dim field with a slow gradient across vast space. In that gradient, the last clumps of matter orbit and settle. Any thin disks of debris soften at the edges. Any shadows grow deeper because the background is so even. A final answer settles the quiet uncertainty of what remains, not spectacle, not sudden endings, only simple processes that never hurry. Expansion stretches, radiation cools, gravity smooths what is left into calmer shapes. The motion continues in the same direction. The quiet deepens without changing its tone.